In this episode, I want to discuss a chi-square goodness of fit. Well, what is chi-square used for? It's used with count data to look at how many different items are in a particular category. And as a result, it's used with whole numbers only. In other words, if you're counting marbles into different boxes, you can't say there are 1.5 marbles in a particular box. And the question it asks is the distribution of the items in the categories different from random? There are two types of chi-square. In this episode, I'm going to talk about a goodness of fit chi-square, and it entails only one independent variable. Therefore, it uses a 1 by n table. So let's look at an example. Consider this test question. Jill loves the taste of coffee. If she could, she would blank everything so it tasted like coffee. Now, people could choose one of three answers: cuffify, coffify, or caffify. And the idea behind it was to see if the a vowel in caffeine would influence their answers. The data looks like this. The row of results just contains the raw answers given. There's no need to calculate the actual counts because the stats package does it for you. And here's the 1 by 3 table with the three values 70, 91, and 155. Question is, are these numbers unlikely to be generated by chance? Let me demonstrate how carrying out a chi-square goodness of fit is done in Jamovi. First, you choose frequencies, goodness of fit chi-square, and then move the results into the variable box. And it turns out that the results are significant, that getting this distribution of numbers would be hard to get by random chance. But one thing that we don't have here is a measure of effect size. Remember, p-values aren't effect size. One nice measure of effect size we can use is Kramer's V. And it's pretty easy to calculate with the results of the study. You just need to know the degrees of freedom, the total number of observations, and we plug it into the Kramer's V formula. In this case, we get a 0.079. Now, Kramer's V numbers range from 0 to 1. So some people interpret the results in this way: a 0.1 to 0.2 Kramer's V is a small effect. And if you look at what we got, it's a 0.079. So we can say that even though the results are significant, they're not very strong. Now, how do you report the results of a chi-square in a standardized format? Well, first of all, you put the degrees of freedom in, and the actual chi-square number, and the p-value, and then add the Kramer's V at the end. What the test tells us is that the actual counts we got are different from what you'd get by random chance. But what we'd like to know sometimes is what the differences between each individual outcome is. For example, were there significantly more people who chose cuffify over coffify, or caffify over cuffify? In order to do this, we need to run 3 different chi-squares with the counts for each outcome. And this is how the data are set up in the spreadsheet. Now, one word of caution. When doing several different analyses with the same data, there's a chance of getting significant results that really aren't significant. And we need to avoid this by doing a Bonferroni correction. And this is a fairly simple thing. All we do is take the number of analyses we're going to do, in this case 3, and divide the 0.05 level of significance by 3, and that gives us a new corrected level of significance of 0.0167. In other words, each of the 3 analyses must reach the 0.0167 level rather than the 0.05 level. To do this analysis, we go to frequencies once again and 2 outcomes binomial test, and we plug our 3 comparisons in. And what we find is that 2 of the 3 are significant. The ones that are significant are the ones that compare the A responses to the other ones. So if we needed to do a chi-square with more than one independent variable, instead of using a goodness of fit chi-square, we'd use a test of independence, which is sometimes called a test of association or independent samples. And that's a topic for another episode.